Okay, I'm Dan White, Valparaiso University, or Valpo. There is a Valparaiso, Chile. We're the one in Indiana, near Chicago. I'm a professor of electrical and computer engineering there, and I've been there, 12 years now. And we have a new space program. The BEACON mission will be our first satellite, and our first satellite will be BEACON 2. And there's a story with that, as we'll do. The lab that I run is called the Wireless Research and Electronic Discovery Lab. There's an embedded joke in there. It's an exclamation point in the front because we don't do wired things, even though in engineering I have the most thousands of feet of cabling for the antenna farm to do wireless stuff. So it's terminating cables is always a fun thing to do when you're doing wireless. All the wires. Okay, so why the BEACON mission? Our institution's mascot is the beacon also, so there's another reference there. Beacons, they're heard by ground station receivers, health and status report for satellites. We're very interested in hearing that our satellites are alive and hear from them, get telemetry, health and safety data. TinyGS has increased a lot with LoRa. Those receivers are listening to packets and decoding them. It's Doppler resistant and such. So TinyGS does a really good job, actually, of catching these sorts of packets, and we've seen lots of PocketQube missions have made use of this. A downside of a broadcast beacon is you don't know the schedule, besides a interval timer or so. It's limited certainty that you're going to actually receive the packet, because we're not tracking where we are or anything like that, and then also very little data that we get down. So bare minimum to just understand the state of the spacecraft. The whole point of a satellite mission is to have data down. If you don't have any data that comes down from the satellite, what was the point? And I know, Kevin, you're push on that with their students. As you design a mission, it's really cool to build a satellite, but we need some justification for the mission. Why does it need to be in space, and so on. Okay, some of our reasons for building a satellite is because we want to and it's cool. So this is a safe group to say so, to say that. If we want more data, we need larger antennas, we need larger bit rates. We have limited ground station contact for our high bit rate radios. If I need to close my link budget because I'm limited on power, I need a narrower antenna. As soon as I have a narrower antenna, I have to point my satellite. And now I have an ADCS of higher capabilities than I needed just for my data. Increases our power, increases our risk. Really, it increases our risk simply because we want to get our data down for a mission success. So, is there a way that we can get more data down without increasing risk? Omnidirectional antennas mean we don't have to care, perhaps, at all about tumbling or other issues. All right, so another place this acronym shows up is the satellite performs broadcast downlink sessions coordinated with scheduled observations on the SatNOG's network. So if we can downlink, send broadcasts of larger bits of data, larger and unique data perhaps, we can, of course, get our data down, but someone has to be listening. The SatNOG's network, in the same way that TinyGS does, actually I don't know if TinyGS transmits, but anyway, SatNOG's does not. It's receive only. I have no handshaking. If it's over a ground station, I can say, please do a bulk download, and we have the handshake happening. With SatNOGs, we can schedule a listening session, and the decoders, the software-defined receiver and decoders are running, but if it's just a beacon, we just hear the beacon packets and that's it. The rest of the time is noise or silence. What if we can schedule the satellite to know that someone is going to be listening, or that someone is most likely going to be listening? We can downlink more data with our cheap and low-risk radios. That's the core of the beacon idea. I just want to say this right now. SatNOG's schedules events in the future, downlinks in the future, all your satellite needs is the capability to send data at a future point. So if it's not over your head, your satellite just needs to send a broadcast downlink at a point in the future. Not everybody builds that capability outside of just beacon packets. So this mission is doable, even perhaps by you if your satellite already has this capability. So why are we doing this? Well, one is to demonstrate that it can happen and show and just kind of work out the realities of how this coordination would work. That's the concept of operations, and then we also have our own space program. We would like to fly a satellite, develop teams. We're an undergraduate institution for engineering, so a continuous pipeline of students that come in with huge life changes from high school through graduate college, and learning. Sometimes I joke that I work with always work with incompetent people. Well, of course, Professor White, I don't know about this. Of course you don't. Why do you think you're taking this class? So it's a perspective change, and it's a lot of fun to watch growth, but also for my point of view, running a satellite mission is we need projects that are low risk anyway, and a lot of us are in that boat. Really advanced PocketQubes, and that's phenomenal, but PocketQubes are also a nice entryway. All right, so if we can do this, we get more data, more budgets of all sorts for mission, and less risk for our teams. All right. I've been involved with SatNogs. It's a crowdsourced network since, I think, 2014 or so. And I've been a Libre Space Foundation core contributor since, I think, 2016, something like that, 2018, when we started that. So happy to talk SatNogs. This talk isn't necessarily about that, but a brief overview of this. I'll click through the slides pretty quickly for this. So this was taken just yesterday, active stations on the network. We also have one in Svalbard and an active one from AMSAT Germany off of Antarctica, but I just can't zoom out far enough on the map. So ground stations all over, receivers all over. These are times that we can schedule downlinks and receive our low bit rate data, maybe 9600 baud or something that's cheap and easy for us. This network, this is kind of a system architecture of it. We have the SatNogs database. That's a database, or machine-readable database of satellites, orbits, transmission parameters, radio parameters and such. We started this database immediately after we started the SatNogs project because there was no machine-readable database of modulation parameters and how to listen to various satellites. Nice websites, but don't try to parse HTML directly. All the ground station owners are independent. This is very much crowdsourced. The software is open source, and the any hardware designs that we spin out also are. Early in the days, there was this rotator, is a 2-axis rotator design, all 3D printed. It's kind of it's not active on it. We're not. You're welcome to build it, but it's a bit tricky to build. So I'm happy to talk about the rotator, but it's not worth it, or it may not be worth it unless you really like to tinker. All right, so that's the architecture. This is what an observation looks like, or the result of an observation. I've been part of the ARIS education committee for several years now. We listen to FM downlink of astronauts on the ISS, doing contacts with schools, Q&A sessions over amateur radio. We get the waterfall. Since it's an audio link, we get the FM or the baseband audio out of this. Additionally, this is for more of the ham stuff. On the other side, this is if your satellite has beacon packets, downloads those. We have, and you're open with the telemetry formats, the decoding of your frames. So the radios can receive the bits in the frames, but if you're open with what the bits mean, then either you are able to, or someone else in the community, just because they want to, will make a dashboard, a Grafana dashboard, and perhaps you've seen this satellite before. All right. Any reception that comes in on the network from any ground station shows up in the database, shows up on these dashboards in mostly real time. So there's a lot of teams, CubeSat teams and other teams that have used this as their, we heard the first beacon. Sometimes the packets come over here. If it's a lower radio, sometimes those first packets are over TinyGS, which to be honest feels a little sad to me, but I'm a SatNogs guy. Anyway. All right, so we move on. Beacon 1. So the beacon mission is demonstrating that we can do this coordination to downlink data to ground stations that cannot talk back, receive only. How do we coordinate this? All right, Beacon 1. So hooked up with the Libre Space Foundation, so it would be natural that we do LSF's cubic design. AMSAT Germany has a pair of VHF and UHF PocketQubes built and I think integrated. I don't remember if they've launched or not, but starting in early 2024, we started building one of these, trying to understand the documentation. When we say open source and someone that didn't design it is reading the documentation, this is always an issue, yeah? Well, I have, remember, incompetent helpers are undergraduate students that are very motivated and learning quickly. So they're learning, reading the documentation. I'm there to kind of give background information, and then one of the outcomes that I like to see is the students improve the documentation. That's a lot of effort because no one wants to do write documentation after you've learned stuff. You just want to move on, throw your homework over the wall, and move on to your next class. All right, so we had a kind of a fit check model just to get an understanding of what the structure looks like. And then 3 weeks later, or 3 weeks after attending SmallSat, just in August, we get a call from this place. They say, hey, you remember our conversation from SmallSat? Yeah, we were talking about high altitude balloons. And that was good. No, the other stuff we were talking about, I'm sorry, I wasn't paying attention to the other projects that you have going on. I was interested in flying high altitude balloons with you. And they're like, you might want to hear us out. Anyway, would you like a free ride on a different platform, not a PocketQube, and deliver in April, which is next month, which is terrifying, and so on. I'm like, we already have a mission. The whole mission is a radio, but this platform from Near Space, called the Dream Big program, is, we'll have a picture of the bus here, it has Iridium radio for the communications. So it's a half-U CubeSat, or half-U CubeSat-like form factor with an Iridium radio, and in a 6-pack of it with six university teams. All right, so it was a good opportunity. It also came with 3 high-altitude balloon flights as part of that. Here's the picture. So this one is from last week. We did a high-altitude balloon launch. That was our second. We'll do another one in April. It's always fun. People are flying glow sticks on this one, toothpaste. There's a whole bunch of insects. There was one toasted insect because it was in a house fire that happened to one of the participants. It was incredible. But they got to take a break from dealing with the house fire to fly a balloon. 3 universities part of this, 3 balloon launches. We were going to already do the balloon launches with Near Space anyway, and there's just, it's been crazy. It still feels like, well, it's been crazy. Okay, so this is from our team's PDR for this program. It's just a nice picture from a balloon launch. Here's what the bus, Near Space, their half-U ThinSat bus looks like. There are 6 of these structures, and they all clamshell together into a 3U CubeSat form factor, and that's the block that gets deployed from the deployer. I don't even know who the deployer is, who the service provider is. But then we are delivering the payload inside of that. Remember, we went from an entire 1P PocketQube from a design that has been on orbit, but not, we're trying to build our own and get in-house expertise on this, to now it's only a payload. Power is provided for us. It's approximately infinite power compared to a 1p, and it's approximately infinite volume compared to a 1p, and we have a ton of empty space now. So we decided to fill the empty space. Let's see, we have our communications board. We pulled that right out of our PocketQube. It's the PQ9 ISH from Libre Space. That's our radio for our mission. We're not going to touch it. We're touching it as little as we can. And then off to the side here, these vertical boards on the side are magnetorquer coils. Well, remember we had lots of extra power budget, lots of truly empty space. We had the antenna on the top. I'll talk about that in a second. And then the 1P PocketQube comms board, a single board, and that was it on this. And it was just empty space. We did not think for more than 12 seconds about mass budget because we were going to be under by a factor of 10 or something like that. It was crazy. Well, just a few weeks before then, we had contacted University of Luxembourg because they were ahead of us flying the same bus, the cubic bus from Libre Space. I knew about this, so we called them up, had a conversation. Hey, you guys learned this and built one and have integrated it with 𝗨𝘀. You know, what did you learn from doing that? We're trying to build our own at the same time. We had some great conversation. Well, 1 week later, that was in between talking to Nearspace, we called them back. I called them back and we said, hey, can we set up a Zoom call? We do a Zoom call and we're like, change of plans. We still want your advice on building a 1P, but we're not building a 1P anymore. We're in fact flying all the internals of a 1P, but now we have unlimited space. I understand that you had an ADCS board and magnetorquer coils on your PocketQubes mission. And they're like, yeah. Would you like to just ship us your engineering model and we'll bolt it onto ours and fly it again? And they're like, that's crazy. How much? Free. It's free for us. All of Nearspace is provided by third-party grant funding for the Dream Big program. So they're like, really? Yes, I do not want to do any university international paperwork. You ship it to us, it becomes ours. We own it 100%. You know, for any issues like that, it's just an ADCS microcontroller board and magnetorquer. So we are going to fly a variant that was on Paquito of their ADCS board plus magnetorquer coils that are just a little different form factor. Their Z magnetorquer coil is, I presume, will be exactly the same as what they flew on Paquito. We have a separate power bus for them that's provided from the spacecraft bus, so we can separately power that off. It's a CAN bus, one-wire CAN communication between it, so if something goes weird or whatever, we have independent power control on the ADCS subsystem, and it's a one-wire CAN bus, and we're only using it for that. So we could not have to work together very closely with Luxembourg, but yet still offer them a kind of a sub place. It's been a crazy time. Remember, we had the Iridium bus, and that was the communication for this. My response to Nearspace when they hit us up for, do you want to fly on this different platform? I'm like, our mission is a radio. Not the radio, not the modulation formats, not even the antenna. It's the operations. It's the idea. So we're kind of flexible on what we can do. But if we don't got a radio to downlink in UHF, which is about 75 or 80 or 78% of the listening stations on the SatNOGS network or have UHF antennas, then we have no mission. And this is late August. We do not have, we just can't design a new mission for this Dream Big program. So they're like, okay, we'll get back to you. They're like, okay, well, if you are the owner-operator of it or something, we can figure out the licensing for this, then we can have a radio on it, amateur band downlink, and then the Iridium side channel. Let me tell you, if you're designing a mission and you have, Mike, you were talking about a Iridium radio on this and on a PocketQube, you have your UHF command and control radio, low bit rate. Maybe it's not for your downlinking your data, but it's like your baseline, it has to work radio. Well, if you have that radio, plus you have an Iridium side channel, it's such a cheat. Everything is so much easier. Well, what happens if we need to do something that requires elevated authorization? It only comes through the side channel. We don't care about work. It's amazing. It's such a hack to have an Iridium radio on a PocketQube. Unfortunately, now we have 2 ways for command channels to go in. It's respin the circuit board and all sorts of stuff. All right, so we can't have any deployables on this. They already clamshell together, and near space is hard requirement. Nothing can extend beyond the rectangle or the box of the payload volume, because this is very important. No deployables, so if you know anything about UHF and even CubeSats, the antenna, whoa. My battery's running low too. The antenna doesn't fit, yeah? Patch antenna, dipole antenna, PocketQubes, we just pop out the tape measure antenna. They're beautiful, and it's fun to do a burn wire demonstration just like every single day just because. It's cool when it pops out, right? It's just an awesome demo. Well, we're gonna fly a slot antenna because then we can make the outer surface look mostly conductive, have a little gap there. Let me tell you, KiCad does not like slot antennas at all. It thinks you're doing everything wrong because everything's just one node electrically. So we found a fractal slot antenna, and it will radiate because it's pieces of metal and we're going to send energy into it. It's not going to radiate very well. But remember, we don't need to close our link budget for uplinking or even downlinking for baseline command and control. We're using the Iridium radio for that. So in this limited time and such, we'll see how it performs. And then students are learning that when we're matching an antenna, just because it matches, it dips because this is small. This is the only thing that fits on here. This thing resonates at like 500 megahertz, 480 megahertz, which is not the amateur band, but we're going to drive it off resonance. Matching is weird. Nothing makes sense. So imagine when you're an undergraduate doing radio stuff, or even now doing radio stuff, and you're trying to match something that has nowhere near resonance, and everything is terrible. So it forces you to understand the first principles. Just a selection of boards. We also have a emulator board here that's been my project. Is to replace the near space bus with something that behaves like the near space bus over the command channel, provides power so that the team can do their testing. Baseboard, we see the PQ9 format for our communications board, the ADCS board, temperature sensors and such, and I suspect, hearing from others, that our temperature sensors are always going to read low instead of high. We're a little worried about transmitters overheating, but maybe that's not going to happen. So that's somewhat good news. We do have blinky lights on there just for fun. All of this, except for, I think there's 2 repositories in here that are not open, but at this link, I have a QR code at the end. I think the next slide for the whole slides. Everything's open source in the LibreSpace way. We just have, let's see, the bus emulator contains near space proprietary stuff, and then the organizational repository is kind of project management stuff and not useful to anybody anyways. So, happy to talk more about this. I really want you to do the mission of downlinking more than just beacons to the SatNOGS network. You can do that now, and in fact, you could probably, there's probably people in this room that could do that demonstration before we deliver this. And I still think that would be awesome. All right, so thank you.